afternoon, everybody. I think we will start
Good
the
afternoon,
class.
sir.
Only 9 members are there still now. I think they will join. We will start the class. Okay, same master answer operation. I would like to continue because we stopped in between. Yeah. In the morning, we have derived this equation. Okay, then for this equation, we have to go further. This is nothing but liquid phase overall mass transfer. Overall resistance is equal to individual mass transfer resistances. Then, okay, this is that equation. You can compare that one. KOL 1 by KOL is equal to 1 by HKG plus 1 by KL. Use that equation. This one. Okay, for this equation, we will use the previous derivations. From there onwards, I would like to continue. Now what we have to do from equation 2, then what is equation 2? We already derived this equation. Na is equal to kg into pa minus pa star. Okay, we can verify from the previous slides. Equation 2. Yeah, this is equation 2. Na is equal to kog into pa minus pa star. So this equation I have written there. Now to continue with the derivation from equation 2. Now for this equation we can write 1 by kog. 1 by kog is equal to, we can write pa minus pa star divided by Na. Same operations, substitute with the interface concentration PI and add interface pressure PAI. So PAI will be there. Now we already know from PA minus PAI, this PA and this PAI, we have to take it out. Then the left out equation is 1 by KOG is equal to PA minus PAI divided by Na. One term, that term we have to take it out. Left out term is PAI and PA star. PAI minus Now left out term will be PAI minus PA star by N. You can verify from the previous equation this one. PAI and this is PA star minus PA star NA. So we already know what is this equation. PA minus PAI by NA is nothing but 1 by kg. We can see individual mass transfer coefficient equation, that is equation number 3. Yes, this one. From this equation, PA minus PAI by NA is nothing but 1 by kg. This is 1 by kg is equal to 1 by kog plus PAI minus PA star by NA. So these whatever the left equations are there, we need to convert them into concentrations using the Henry's law. What Henry's law is saying? Henry's law is saying wherever the partial pressures are there for the component A, it is directly proportional to concentration which is in equilibrium with that partial pressure. Okay, the proportionality constant in this one is H, which is Henry's law constant. We can say Henry's law constant. At interface from PPT, you can verify this one. See, PA is equal to H into CA star, we can write. Similarly, PAI is equal to H into CAI, we can write. Here also PA star is equal to H into CA, we can write. So this is what the Henry's law is stating. So then we can write this one H into CA star, and similarly at PAI is equal to H into CAI, we can substitute. In this equation, see, instead of PAI we can substitute H into CAI. In place of PA star we can substitute H into CA. So next terms will be 1 by KOG, 1 by capital KOG is equal to 1 by kg plus, in place of this PAI we can substitute H into CAI. HCAI, in place of PA star we can substitute H into CA divided by NA. From this equation we can take H common because in the both variables H is there. This 1 by KOG, this is 1 by kg. We can take H out. So left out term is CAI minus CA by NA. Now from equation, previous equation, CAI minus CA by NA, we can substitute 1 by KN from equation 4. So here Yeah, from this equation, see CAI minus CA, we can write 1 by KL. Same we have to substitute there. So in place of this CAI minus CA, we can write 1 by KL. So the left out terms will be 1 by KOG is equal to 1 by kg, plus H is already there. In place of CAI minus CA by NA, we can write 1 by KL. So this is the relationship between overall gas phase mass transfer coefficient and individual mass transfer coefficients. Okay, this is overall gas phase mass transfer coefficient. This is individual gas phase mass transfer coefficient, and this is individual liquid phase mass transfer coefficient. This is the relationship between overall mass transfer coefficient in gas phase to the individual mass transfer coefficient in the two phases. Similarly, previously we derived yeah, this is overall mass transfer coefficient in terms of liquid, relationship between overall mass transfer coefficient and individual mass transfer coefficient in two phases. Okay, these are the two equations. One equation is for the overall mass transfer coefficient in liquid phase, and next one is overall mass transfer coefficient in the gas phase. So these two equations are very much important in solving problems. At the same time, this derivation is also asked many times in your previous question papers. Okay, then I hope if you don't understood still now also, just open your pen and open your book and write with your pen. And if you derive on your own, then only you can understand. Okay, there are two cases, frequently encountered special cases in this type of equations. So these are two derivations up to, until now we have derived these two equations. Now we will see what are the special cases. Now special cases are when the gas is highly soluble, then the resistance to mass transfer, MT means resistance mass transfer. Okay, when the gas is highly soluble, okay, gas is highly soluble means this phase is highly soluble in the liquid phase, then the resistance to mass transfer will lies in the within this gas phase region. So what happens, the gas is highly soluble means the coefficient will be very high, whereas resistance will be very less. So we can cancel out the resistance offered by liquid, because large part of this resistance will be there in the gas film only. So we can take overall gas transfer mass transfer coefficient is nothing but individual gas phase mass transfer coefficient, we can say. So this is this term 1 by KOG is equal to 1 by kg. So we will just equate them, then we can obtain KOG is equal to kg. Overall gas phase mass transfer coefficient is equal to individual gas phase mass transfer coefficient. Okay, this is for the case of highly soluble gases, So example for these highly soluble gases, we can take the same example. NH3 plus air is there, in which NH3 is diffusing into water. So NH3 is highly soluble in water. So we can take for the highly soluble gases like NH3 in water, we can directly use this equation. Instead of this complex equation, we can use this equation in which only one individual mass transfer coefficient is enough in order to calculate the overall flux. And another case is for sparingly soluble, meaning less soluble gases. Okay, like we can say oxygen is less soluble in water. For example, we can take the example of oxygen, which is very much less soluble in water. So we can take that example. So for less soluble gases in liquids, so large part of this resistance will be offered by this liquid film. So liquid film resistance will be very high compared to this gas film resistance. So in that case, we can cancel out the gas film resistance term. Only the liquid film resistance terms can be used directly. Okay, instead of wasting our time in calculating KL and KG both, we can directly use, when we can understand that that's a particular gas in operation is uh, highly soluble means we can directly use this equation instead of waiting for calculating these two mass transfer coefficients. Okay, when gas is very low soluble, instead of waiting for calculating these two coefficients, we can directly use only one coefficient, estimate one coefficient, and put the overall coefficient to the one coefficient equal. then our system will be largely simplified. For the intermediate solubility of gases, we have to evaluate the both terms KL and Kg. Okay, for these two special cases, we can use directly these equations. We need to remember that one, this one. So this is the special cases. So I hope this understood. Otherwise, just watch video one more time. Anyway, I'm just uploading the same videos every day in the channel. So MTO channel. So please do watch that. So next topic in this one is wetted wall tower. Estimation of mass transfer coefficient through wetted wall tower. Okay, estimation of mass transfer coefficient through wetted wall tower. This is the last topic in your unit 1. Okay, so we will use some empirical correlations here in order to evaluate the mass transfer coefficient. We already know what is mass transfer coefficient. Mass transfer coefficient is denoted by small k, so which have a many forms like gas phase mass transfer coefficient, liquid phase mass transfer coefficient. For the A through non-diffusing B, one type of mass transfer coefficient, and next one is case of equimolar counter diffusion. We will have another type of mass transfer coefficients. The notation scheme is almost same, but variation in dAV by RT, other formulas. Okay. So here mass transfer coefficients will be evaluated using the empirical correlation. These empirical correlations are nothing but somebody has conducted experiments with large number of liquids or gases. Then they concluded that every mass transfer coefficient will be varied in such a form that every mass transfer coefficient will fit in this equation. So these are known as correlations. Okay, these are experimental facts. Okay, these are not a theoretical facts. These are not from any theory. Only these are derived from the experimental facts. Now the first case is this equation. SH is nothing but Sherwood number. Sherwood number is equal to 0.023 NRE power 0.8 SC power 1 by 3 nu by nu W power 0.14. This is applicable for the mass transfer in pipe walls in case of turbulent flow. Okay, similar equation you can see in the heat transfer also. We popularly known as Dittus-Boelter equation, Cedar-Tate equation. Okay, this is a Cedar-Tate equation. In heat transfer, instead of Sherwood number, we can write Nusselt number, NNU we denote. Instead of this SC with the Smith number, we can write Prandtl number. Okay, in heat transfer, comparatively, if you can correlate these two, then we can write here Prandtl number in heat transfer. So here, instead of Sherwood number, we can write Nusselt number, NNU. NNU is equal to 0.023 NRE power 0.8, PR power 1 by 3, nu by nu W by 0.14. Same equation will be present in the heat transfer. You can see during the convection heat transfer, you can see this type of equation, whereas only the is replaced by Prandtl number. Now for the mass transfer concern, we will use this equation when the mass transfer is taking place in pipe walls in case of turbulent flow, which is Sherwood number is equal to 0.023 NRE power 0.8 SC power 1 by 3 nu by nu W power 0.14. This is a viscosity correction factor. Okay, due to viscosity will be varying with for wall for the reactor wall or for the mass transfer column wall, the wall will have certain viscosity. In order to correct those viscosity between the fluid and wall, this term has been incorporated. This is viscosity correction factor nu by nu W, in which this one Sherwood number SH is known as a Sherwood number. The Sherwood number you can see KD divided by DAB, where K is the mass transfer coefficient. This small k denotes mass transfer coefficient, mole per unit area second into driving force. Whose units are mole per unit area unit time and into driving force. So this D is diameter of the tube or column. Okay, this is the D. Small d is the diameter of tube or column. And DAB, you already know, this is the diffusivity of A through B, which has the units of meter square per second. So sorry, it's a meter square per second. Yeah, meter square per second. And D is the diameter of the tube, which have a units of meter. And then Reynolds number in the formulas in this one, the formula NRE you already know from the fluid mechanics. NRE is equal to dV bar rho by nu, in which D is the diameter of the tube. Okay, we can change this to the diameter small d, since we are denoting in Sherwood number. This is small d. So dV bar rho by nu. In this, d is diameter of the tube, v is velocity of the fluid, rho is the density of the fluid, and nu is the viscosity of the fluid. Then Smith number, SC denotes the Smith number. Smith number is given as nu by rho dAB. In this, nu is viscosity of a fluid, rho is the density of the fluid, and dAB is diffusivity of A through B. Then nu by nu W is the viscosity correction factor, in which nu W is the viscosity of the wall, particular mass transfer wall. Then this is the second case, the second formula, which is applicable for the evaporation of liquids in wetted wall type tower. So the example for this is evaporation, what we call humidification. Humidification is nothing but transfer of water from liquid phase to the vapor phase, is nothing but a humidification. We will add the vapor phase of water to the surrounding air, is nothing but humidification. For the humidification type of cases, we will use this formula instead of this viscosity correction factor. We will neglect the viscosity correction factor and we will use this formula. Okay, these two equations are used to calculate the mass transfer coefficient. These two are the correlations. These are the experimental facts, not the theoretical facts. And this is the wetted wall tower. Here you can see wetted wall tower. It is nothing but absorption tower, we can call. It is composed of a shell around the diameter 1 to half meter diameter, something will be there, in which the materials like packing materials, some packing materials, some plate columns, some bubble cap trays like materials will be there in this one. You can see here the both gas and liquids will flow counter current to each other. See, gas is letting inside here from the bottom, whereas the liquid is getting inside from the top. Okay, where L, G, here also the G and L are nothing but a gas flow rates whose units are mole per second or kg per second. Whether we are considering the mass terms, we can use kg per second. When we are considering the mole terms, we can use mole per second. So here you can see the gas is getting inside here and it is going outside from the top, whereas liquid is getting inside from the top and it is going outside in the bottom. So here the concentration of component A in liquid phase at point 2. If you consider this is point 2 and this is point 1, inlet point for the gases. Since here the mass transfer is taking place from gas phase to liquid phase, we will consider the first point, inlet point of gas, as a point 1, so that our variables in the mass balance will be same. Mass balance or the component balance will be equal to each other. So here you see gas at inlet flow rate of g mole per second is entering at point 1 with a partial pressure of gas as Pa1, whose equilibrium concentration in the liquid phase will be Ca star. From the Henry's law, we can write Pa1 is equal to H into Ca1. Okay, Henry's law is applicable for dilute gas solutions in liquids. Okay, from Henry's law, we can write Pa1 is equal to H into Ca1 star. Okay, where Ca1 star is the equilibrium concentration in liquid phase. Then Ya1 is the mole fraction of a component A in the gas phase. And then Xa1 is the mole fraction of equilibrium, Xa1 star. This is Xa1 star is the equilibrium mole fraction of that component A in the same liquid phase. Okay, then the inlet gas will be flowing from the top of the tower, where L is the moles of molar flow rate or the mass flow rate. When mass is used, kg per second. When moles are used, it is mole per second. Mole per second of liquid is just entering from point 2 with a concentration Ca2, whose equilibrium partial pressure will be Pa star, Pa star, Pa2 star. So from the Henry's law, we can write that Pa2 star is equal to H into Ca2. Yeah. Then equilibrium mole fraction in the gas phase can be expressed as Ya2 star. Then the final gas will be out in when some part of the solute from the gas is dissolved in the surrounding liquid. The final gas will be going out from the top of the tower, in which the G gas flow rate will leave from the top, in which for the convenience of mole balance, we will keep G, L and L. Everything is constant. Flow rates are constant. Only the compositions or the concentrations are varying, not the flow rates are varying. So here the PA2 is the partial pressure of component A at point 2, and CA2 is the equilibrium concentration of this component A at point 2, and YA2 is the mole fraction of component A at point 2, and XA2 star is the equilibrium mole fraction of component A in liquid phase. Then L is the mole fraction of, then the after the operation, the whatever the liquid will take some part of the solute from the gas and come outside. So the coming outside liquid will have a flow rate of same, which is same as that of inlet LL, whose units are mole per second, and the concentration at this phase is Ca1, and the partial pressures, equilibrium partial pressure is Pa1 star, and the mole fraction in the liquid phase is Xa1, and similarly the equilibrium mole fraction in gas phase is Ya1 star. So these are the notation schemes which are applied for the wetted wall tower. So the liquid will just flow like this one. So through the wall, okay, by supporting this wall, the film will be formed inside. Through this film, when the gas is inlet, through this film the mass transfer will take place. Throughout this film, the mass transfer will take place, and the concentration of this component A in gas phase and liquid phase will vary. So the compositions observed in inlet and outlet will be different. Okay, whereas only compositions are varying, partial pressures and compositions are varying. So from the mole balance, okay, what is the mole balance? Already we know what is the component balance. Component balance is same as that of the mole balance. So from the mole balance we can say output minus input plus accumulation is equal to uh, rate of generation. So from this mole balance we are considering it steady state. Steady state means there is no accumulation we can keep zero. Okay, then no chemical reaction means we can keep generation term zero. So the final equation left out will be output is equal to input. Output rate of mole is equal to input. So we will derive this equation. Yeah, in the wetted wall you have seen that input is equal to output. The mole balance will be, just wait, I am creating one more library. It's not lovely. Yeah. In the wetted wall tower, you already see if it is not coming, live load is not coming. Well, you can see here, we can balance the equation throughout here. From mole balance, we can write input is equal to output. So from input is equal to output, we have to just go to figure. Now you see inlet is this one, liquid inlet is this one, and gas inlet is this one. So inlet liquid rate is L and gas inlet liquid rate is G. So, so liquid rate sorry, liquid rate at inlet and outlet both are same, and to gas inlet rate and liquid inlet rate are both are uh, same. So the component balance we have to write. The component balance is for writing, we would write for only component A. So L into, in terms of mole fraction, we can write L into XA2, which is inlet. Okay, L into XA2, L into XA2 is equal to plus for the gas G, L into XA2, this one L, this L, and XA2 this one for the component balance, and inlet at the same time gas is inletting from here, G into Ya1, G into Ya1, G into Ya1. So small x, this is small x, this is small y. So G into Ya1 is equal to output. So output here is, you can see G into Ya2 is the output gas and L into Xa1 is the output liquid. Ya2 plus L into Xa1, L into Xa1. So this is the component balance. L into Xa1 we have written for the both gas and liquid. So we have to just interchange the variables. Now all G will bring on one side and all X will be on one side. All L will be on one side. Now L into this one, L into Xa2 plus we will bring this to that side. So here minus it will become V. So Lxa2 minus is equal to so Gya2 into Ya2 minus it will become minus Gya1. G G into Ya2 minus Ya1. Now what we can do, we can take common, L we can take common. L we can take common from here. So this same we will apply here. So this is Xa2 and this is equal to, we can take common. This one equation, whatever the equation we have derived this is same as this equation. This we can keep this as a mass flux. So here we are indicating this one as molar flux. Molar flux here bar we are keeping because it is not in the flux type. So flux will have a units of mole per meter square second. So we are not considering the area of the tower. So we are keeping this as Na bar. Na bar means which have a units flux which have a units of mole per second only. When we multiply this with we divide with A area, this equation will become Na, true flux, which will have a units of mole per meter square second. Usually the mass transfer coefficient or the flux will be expressed in uh, mass transfer coefficient into driving force. We have seen this earlier, mass transfer coefficient into driving force, whether it may be this driving force may be concentration gradient or pressure gradient. Whatever the other terms apart from flux and driving force, the left out terms are called mass transfer coefficient. So mass transfer coefficient, since this is a counter current flow, so counter current flow, in order to compensate this driving force, okay, true driving force will be considered in terms of logarithmic mean pressure difference or logarithmic mean concentration difference, or the logarithmic mean mole fraction difference. So you would you may see this equation, this type of equations in heat transfer also, where you can see logarithmic mean temperature difference in the counter current heat exchanger or in cross flow heat exchangers. You will encounter the logarithmic mean temperature difference. Similarly, here also in the counter current operations like this absorption operation or a wetted wall tower operation, we have to write the mass transfer coefficient into the logarithmic mean of driving force. Whatever the driving force, whether it may be pressure gradient, whether it may be concentration gradient, whether it may be a mole fraction gradient. So Na is equal to KOG into delta PLN. Delta PLN is defined in such a way that delta P1 is minus delta P2 by Ln delta P2 by delta P1. So delta PYLN is same. Instead of P1, we are writing Y1 Y1. So what is this delta Y1 and delta P1 and delta P2? Delta P1 and delta P2 is nothing but these pressures. So here at point 1, you see PA1 minus PA star, PA1 star. Okay, these two difference, the difference between the partial pressure, two partial pressure at inlet to the equilibrium partial pressure at the outlet. Okay, this is the delta P1. Similarly, delta P2 is nothing but the true partial pressure of component A at point 2 minus equilibrium partial pressure of component A at point 1. Delta P2, PA2 minus PA2 star. This is delta P2. And similarly, delta Y1 is this one, delta YA1 minus YA1 star, and delta Y2 is YA2 minus YA2 star. This is defined. So just to calculate the relationship between PA1 and CA1, CA1 star, there is a Henry's law equation. I already said you the Henry's law equation is PA1 star is equal to HCA1 star, because these two concentrations and pressures are in equilibrium. So then only we can write. We can't write PA1 is equal to H into here PA1 star CA1 H into CA1 we can't write, because these two variables are in contact with each other, or these two are in equilibrium. The liquid phase and gas phase are in equilibrium here. So in between these two variables only the Henry's law is possible. So Henry's law is given here as PA1 is equal to H into so PA2. Here also PA2 star is equal to H into CA2. So all these equations, using these equations and together with all these correlations, we can estimate the mass transfer coefficient. This one K we can estimate. For estimation of mass transfer coefficient, this wetted wall towers will be used. Wetted wall towers are nothing but a absorption column in which they are filled with some packing material or some plates like bubble trays, sieve trays, everything will be filled inside, so that the liquid and gas will come into contact with each other. When we are just incorporating all this liquid and gas here, the transformation will take place through this film. The gas and liquid will flow counter the this counter current activity. We will use the logarithmic mean of this driving force, whether it may be a pressure driving force or it may be a concentration or a mole fractions. Any driving force will be taken in a logarithmic approach. So here the logarithmic approach will be used, so the formulas will be applicable here. So in order to calculate the equilibrium partial pressures using the concentration, we will use the Henry's law. So this is overall unit 1. Yeah, do you have any doubts?
No, sir.
No doubts. Okay. One session we will use for revision of this, quick revision for this chapter. Yeah, okay. I have given one file in your chat box. Just see it. Yeah, it is nothing but a theory and derivation question bank from your old question papers. So answers for this one, everything was given in the notebook. Just you have to go through it. I will give assignment from these questions only. Then already I have uploaded that problems which are already solved problems. I uploaded to your teams. Just go through that one also. Then apart from these 21 questions which are problems are there, 21 problems, and this 12 theory or derivation questions are there. All these questions are from unit 1 only. So from these questions I will make a groups, 2-3 groups, then I will give a assignment so that you can solve all these questions. Whoever are writing the notes, they are exempted from writing the assignments. Okay, who are not writing the notes, they have to write an assignment and upload on the teams. Okay, is it clear?
Yes, sir.
Yeah, everybody please download this one, theory and derivation question. This is the overall question banks already from your old question papers only, nothing more than that added. So just go through this one. I think everybody download the problems, solid problems.
Yes, sir.
Yeah, the solid problems are very much important. I would like to upload this also, your old question papers. Old question papers, it is having a huge data. All how to upload this one. I will try to upload that one also. But this is the questions overall. I just refer. These are the questions. Just we have to go through that one. Only 17 members are coming to the class. Third hour, they are not coming. Okay, if you have any doubt, just go through it. Only 9 minutes are left, so that we can have some topics, discussion about some topics. Anybody? Number 26. 26. I'm not asking attendance. I'm just asking to speak. Number 26. Okay, 28. 28. 28. Okay, 28 is absent. Okay, number 1.
No doubt, sir.
Nothing. Okay. And what is fixed first law of diffusion?
N of A is equal to minus DAP dou CA by dou, dou
Okay.
X.
Not n of a, it is NA.
Okay, sir.
NA, but it is not NA is equal to minus DAB dou CA by dou T. It is JA. Okay, NA separate relationship is there for JA and NA relationship. That is known as relationship between fluxes. You just go through the notes.
Okay, sir.
Number 2. Yeah, what is the relationship between fluxes?
Hello, sir.
Yeah, yeah. What is the relationship between fluxes?
Sir, if you don't mind, a little louder.
Yeah, yeah. Okay, what is the relationship between fluxes?
Uh,
Hello? Next, number 3.
Sir,
Yeah, relationship between fluxes.
flux is
Okay, what are 2 types of fluxes?
Ni mass
Ni mass. Ni and Ji.
yes, sir.
Okay, then what is Ni? Just prepare, and in the next class I will ask. Okay,
Reference frame.
reference frame. Okay, Ni is stationary reference frame. Then Ji is arbitrary reference frame.
Arbitrary reference frame.
Okay, then what is the relationship between them?
Relation between means mass.
What? Mass Na is equal to Nxa plus Ja. Na is equal to Nxa plus Ja. Okay, fixed first law of diffusion is Ja is equal to minus dAb dose
Equal to
dose. Okay, these 2 equations you have to remember. Just go through it, otherwise you can't derive the formulas. Okay, next one. Please put off your mic, and next one, number 4. The relationship between fluxes.
N Ni equal to Nxi plus Ji, yeah, sir.
Yeah, okay. Then first law of diffusion, fixed first law.
Fix first law, sir.
Yes, yes.
Na is equal to minus dAb dou Ca by dou Z.
It's not Na, it's
J,
Ja.
sir.
Yeah. Okay. Then yeah. Okay. Next one, number 5.
Yes, sir.
Yeah. What is the relationship between fluxes?
Ni equal to Nxi plus Ji.
Ji. Fixed first law of diffusion.
J equal to minus dAb dou Ca by dou Z.
Okay. Yeah. Keep it up. Next study well. Number 20.
Yes, sir.
Yeah. Relationship between fluxes.
Na is equal to Nxi plus Ji.
Na is equal to Ni is equal to.
Na is equal to Nxi plus Ji. Hello. 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 Yes, sir.
Ni is equal to
Nxi plus Ji.
Nxa plus J. Fixed first law of diffusion.
J equals to minus dou Ca by dou Z.
Minus DAB. Where is DAB?
Sorry. Minus dAb into dou Ca by dou Z.
Okay. Next one, 23. 23. Okay. 23 is option 26. Please don't raise your hand. 26. Just come online. Okay. Same problem. 29. 29. Okay. Next one, 32. 32.
Yes.
Okay. What is fixed first law of diffusion? Yeah. Next one, 34.
Yes, sir.
Fixed first law of diffusion.
Ni
Okay, nobody is maintaining notes. You could understand that one. Okay, I will leave up to you. It's up to you whether you are maintaining notes or whether you are listening or not. I don't know. But if you are not listening, it's up to you. 49. 49. It's not about raising your hand. Please respond. Okay, 49 is absent. DCT 49. DCT 49. Yeah, not responding. Okay, no problem. I hope you understood the class. Okay, if you didn't understand any class, just go to the previous videos of the channel, MTO channel, with the whose link I already shared. So watch once again and just maintain your proper notes. Okay, I will give assignment. Those who are writing notes don't need to write an assignment. I will give separate assignment to them. Those who are not writing the notes, they have to write an assignment and then they have to scan and submit to the through Teams or any Google Forms. Okay. Okay. Thank you. Bye.